Welcome back to che205. In this video, I'll be talking about stability of numerical solutions of ODEs, or ordinary differential equations. In the last lecture, we talked about briefly the stability analysis of Backward Euler. In this video, we're going to continue that discussion and look at what would be the delta t or delta x, or the increment in numerical solution of partial differential equations or differential equations such that the solution doesn't become unstable. So we started with a generic equation. This is like a toy model, and we always test the stability of any method using this toy model, or in other words, it's a toy differential equation. Okay, so the solution to this is an exponential function, so we know that from before. We test our numerical solution against this. We compare it with this and see how off we are with respect to this exact solution. So if you do the Backward Euler, we showed last time that we get an equation or iterative equation like this, where we start from y0, we get y1, then we plug in y1 here, we get y2, then we plug in y2 here, we get y3, and so forth. And we discussed that if this is supposed to be accurate, then the yn plus 1 should be smaller than yn. In other words, yn should decay, because the exact solution decays in time. You can see that if a is positive, as t goes up, then exponential goes down, the function decreases, right? So yt decreases. If that's the case, then yn plus 1 should be less than yn. That gives us a condition that the magnitude of 1 minus AH should be less than 1, which means I can easily put the condition like so. If I make this a bit bigger, let's make it 14, even higher, maybe 16. Okay, so the condition would be absolute value of 1 minus A times H. Okay, this should be less than 1, because if it's bigger than 1, every time we multiply yn by a number bigger than 1, then yn plus 1 would be bigger than yn. So that means y1 is bigger than y0, y2 is bigger than y1, y3 is bigger than y2, and so forth. So that means our y is going to increase, and that is in contrast to the exact solution where y decreases. Okay, so this is the condition. If you open this up, this gives us two conditions. One is 1 minus AH less than 1, and 1 minus AH is bigger than minus 1. Let's open up the first condition. So 1 minus AH less than 1 means minus AH less than 0. This is always true. So this is always true, so no problem here. Let's open up the second condition. If you open up, let me see where I can put that, maybe over here. If you open up the second condition, right, this condition right here, then it tells me that AH should be less than 2. And that's exactly the condition we have here. AH should be, so AH should be less than 2. Okay. So now let's see where the yes. So the condition so far is AH less than 2, but also if AH is bigger than 1 and less than 2, then 1 minus H over here alternates its sign, right? So if AH is bigger than 1, then this is negative, right? So let's say y1 is negative times a number times y0, and then y2 is going to be negative of the same number times y1, and because y1 was negative, then y2 becomes plus, and then the sign on yn is going to alternate as we go along, or as we increase the n. In other words, if I write it, let's say y0 is positive, then y1 becomes negative, then y2 becomes positive, then y3 becomes negative, and so forth. Right? So that is where AH is bigger than 1 and less than 2. And that actually gives us an unstable solution, because the solution is going to go up and down, and it's going to go plus minus, and we know that the solution is not like that. The solution is exponential, which is a decaying function. It starts positive and it stays positive all the way as the time increases. So we get a condition that AH should be actually less than 1. So we're going to change this to AH less than 1, and of course bigger than 0. Because A is positive, H positive, so then AH is always bigger than 0. Alright, so that's the end condition, which makes the solution stable. So now let's look at the result. If AH actually doesn't satisfy this condition, I want to visualize how the stability looks like. So let me go back to example, I think that's 5.1. So, okay, let's open. Okay, so I'm going to open it up. Let's see here. Okay, so this is the example I saw in the last lecture. Now in this lecture I'm going to change my A times H to see how the instability occurs. Okay, so what is this equation we're trying to solve? So let's actually start with the toy problem. All right, so here is an example. This is the solution to the toy problem using forward Euler. My dt is 0.1 and I set a equals to 1. Okay, so this is basically the a, and the h is our dt. So the point is to show where AH is less than 1 and 2, we get oscillatory solution or unstable solution, and if it's less than 1 and bigger than 0, we get stable solution. So okay, so here's a, here's dt, a times dt or a times h is 0.1 is less than 1, and you see that the green, which is the numerical solution using forward Euler, pretty much follows the exact solution, which is the red curve. Now, if I change my a and increase a such that a times dh, right, becomes bigger than 1, you see what happens. So I'm going to make it 2. Okay, now you see a little bit deviation. I'm going to make it 5. Deviates more from the exact solution. Again, red is the exact and green is our numerical solution. I'm going to make it 10. And you see that a little dip shows up here. So right now is a times h is 1, right? It's right at the border. So if I go above 1, the solution should be unstable. So I'm going to make it 20. That means a times dt is 2. And make it actually 11. So the dip actually becomes deeper. Make it 14. See the oscillations show up initially. Make it 15. More oscillations. Make it 18. More oscillations. Make it 19. You see the oscillations are propagating through the solution. So the red is the exact, and you see the green goes like this. And if I do 20, it goes all the way through and it never decays. So the green never decays to 0. And that's because a times dt is bigger than 1. See, a times dt is bigger than 1. So that's what I mean by unstable solution. So green is unstable, right? It never reaches 0 at long time, where the exact solution reaches 0 very quickly. Okay, so let's look at, this was a stability analysis of forward Euler. We can go ahead and do the same stability analysis for backward Euler or for trapezoidal method that we talked about last time. So, okay, another topic of interest here is the accuracy. So stability is different from accuracy. Now if you do the, let's say if you do the backward Euler, So in backward Euler, we have the condition like this: the yn plus 1 is equal to y over 1 plus h times y, and this is what we found last time. Okay, so, and we know that for stability analysis, the coefficient, the prefactor here should be less than 1 and bigger than 0. Okay? So if you set this to less than 1, because a is positive and h is positive, this is always less than 1, because denominator is always bigger than 1, right? Because a is positive, h is positive, right? A is the coefficient, by definition a is positive. H is dt, dt is always positive or delta t. So downstairs is always positive, bigger than 1. 1 over that is going to be less than 1. So there's no condition for backward Euler. Backward Euler is always a stable regardless of a, as long as a is positive. Okay, the reason is because this prefactor is always less than 1. Let's go to the trapezoidal method. In trapezoidal method, what we found last time was the relation between yn plus 1 and yn was like this, and now for stability, the prefactor, which is this fraction, or this ratio, this should be less than 1 and bigger than 0. Okay, and if you do that, you get two conditions, right? Because you have two inequality to satisfy. One is this should be bigger than 0, and second, this should be less than 1. Okay? So if you do that, you get the condition for a over h. It should be bigger than 0 and less than 2. Bigger than 0 because if ah is less than 0, then this becomes bigger than 1. Right? You can easily see that. If ah is bigger than 0, if it's less than 0, the numerator is bigger than the denominator, and then this becomes bigger than 1. And ah has to be less than 2, because if it's greater than 2, then the solution is, so the prefactor is negative, and if it's negative, the same oscillations happen with the forward Euler is going to happen here. Okay, so the condition has to be this, and you can easily test it with the same spreadsheet that I've created here for forward Euler. Okay, so let me show you the last thing here. For trapezoidal method, the AH should be between 0 and 2. Okay, so let's go back to a spreadsheet and extend this for trapezoidal method. Okay, so here is the spreadsheet for solution of the toy problem using trapezoidal method. I just want to show you that if a times h is not within this interval, then the solution is going to be unstable. So 0 to 2, remember that. Okay, so a times h, which is now right 0.1 times 0.1, is definitely between 0 and 0.2. Between 0 and 2. So I'm going to increase this to 1. Alright, and you see the difference between the exact and numerical solution. It's a bit more now. I'm going to make it 5. Okay, I'm going to make it 10. So right now, a times dt is just 1. It's still less than 2. Right? So I'm going to make it 20. That's about 2, and at this point we are ready to get unstable. So if I make it 25, you see that the solution, actually this is too much. Let's make it 21. Let me go back to 20. Okay, 20 is okay. Let's go to maybe 20.1. Well, not so much. 20.5. And you see that. You see the oscillations start growing. This is just slightly above a times dt, equal 2. Slightly above that, you see that the solution becomes unstable. Okay? So I hope this clears what I mean by stability and unstable method. So realize that backward Euler is always stable. Forward Euler and trapezoidal method have some condition for a times h or a times dt to be stable, and a again is the coefficient in the differential equation in the toy problem. So just to remind you that a is the coefficient right here. Okay, so thanks so much for watching. Stay tuned for the next video on accuracy analysis.